Okay, thank you. Welcome everyone to this Introduction to OpenFOAM course. We're going to be using the ACES cluster. My name is Bjorn Winden. I'm with High Performance Research Computing at Texas A&M University. This is an agenda for today's course. This is mostly a hands-on course where we will log into the cluster and we're going to run OpenFOAM and look into the basics of OpenFOAM in terms of settings and files and commands and stuff like that. But I'm going to start with a little bit of background just so that everyone is familiar with what OpenFOAM is and what OpenFOAM isn't, how it's kind of a little bit different from other CFD software that you might have been using, and go over kind of a visual overview of the basic structure of an OpenFOAM case, because OpenFOAM is not a very visually pleasing software to work with. It is text-based, so it's nice to get a kind of an overview before we dive in. When we go to the hands-on session, we're going to be running a basic tutorial. Tutorials in OpenFOAM kind of run themselves. You just have to push a button and it does all the steps for you. But we're going to be doing it step by step, just so we're sure that we know what's going on. We're going to do a little bit of post-processing with ParaView. We'll have a little bit of a break. I'm not sure if the break is going to be right where it says it's going to be here, but it's going to be at some point in about an hour. Then we're going to be, after that, we're going to be focusing a little bit more on customization, how to modify a tutorial case to suit your needs, and running OpenFOAM in parallel. Implementing new methods, I will talk through it. We'll do it hands-on if we have time. But I should say that with all the hands-on steps, there is an instruction document, which I will show you once I finish this presentation. If you have already located the course homepage, you can find it there and look at it right away. If not, once I finish this basic, like the background introduction, I'm going to show you where it is and where to find it. And in that document, all the commands that I'm doing, all the buttons that I'm clicking, all the windows that I'm opening, all of those steps are described step by step in that document. So if at any point you lose me or there's something that you want to go back and try again, you can do all the steps by yourself. And we're going to end with a Q&A session. Just very quickly about my OpenFOAM background. I started using it in 2010. Back then it was version 1.7. I've been using it almost exclusively for ship hydrodynamics. That's high Reynolds number flows, 1 million to 10 billion. It's multi-phase. There's rotating propellers and interaction between rotating propellers and rudders and moving hulls. So it's very complex problems, and OpenFOAM has been kind of invaluable to me in this journey. In terms of being able to customize the solvers and doing custom setups. I'm currently a professor in ocean engineering, but I'm here speaking today as a faculty liaison in the High Performance Research Computing group here at Texas A&M. So what is OpenFOAM? So first of all, foam, it has nothing to do with foam, even though I'm sure you can simulate foam with it. FOAM stands for Field Operation and Manipulation. So it's basically originated as the foam library for solving field equations. This was back in the 90s. So at its core is some numerically efficient methods for solving linear systems of equations, large linear systems of equations to solve differential field equations. One thing that made OpenFOAM more successful maybe than other such libraries is that it was based on C++ rather than Fortran. Fortran was kind of the go-to thing back then. The fact that it's based on C++ means that it's a lot more modular and easily expandable. It was so successful that they released it under the new public license in 2004 and called it OpenFOAM. Since then, that was 20 years ago, it's grown to a huge community-driven toolbox of methods. The foam, the field operation and manipulation is still the core of it. But it's expanded with a lot more tools and numerical models. It's used mainly for CFD, but you can also use it for other things that benefit from the linear matrix solvers. OpenFOAM is not one program. It was released as open source, so anyone can copy it and make it their own and modify it. So there are a bunch of different development tracks, both commercial and open source, and we'll talk about that a little bit later. A commonality between most of them is that they run on a Unix-like system, like Linux or Mac, or any other Unix system. There are some exceptions to that as well, which again I will go into. So this is an overview of the main development tracks of OpenFOAM. We have OpenFOAM version and the number, so version 1, 2, 3, 4, 5. We're currently up to OpenFOAM version 12. That's the original part of OpenFOAM, and it's run by the OpenFOAM Foundation, which is a non-profit. Then we have a more commercial track, which is OpenFOAM version and then year and month. Latest version there is OpenFOAM 2406, so from June this year. So this is commercial, but it's still open source and free. It's commercial in the sense that the company offers some training and troubleshooting and other things if you purchase their services. Then there's Foam Extend, which is led by some of the original foam developers. I guess they felt that when OpenFOAM, the release of OpenFOAM versions became more structured, it became a little bit harder to quickly implement and try experimental new methods. So by extension, the OpenFOAM Extend has a lot more user-made and a little bit experimental methods. So I wouldn't say it's unstable, but it's definitely less stable and reliable than the more structured versions with more structured releases. But if you're looking for some novel numerical methods, you're likely to first find them in Foam Extend, then they probably will make their way to the main release versions a little bit later. And then, as I said, anyone can copy the entirety of OpenFOAM and modify it and call it their own. So there are a bunch of in-house and other commercial and non-commercial ventures that have their own versions of OpenFOAM. Just an example from my field, ship hydrodynamics, the US Navy have their own version of OpenFOAM that they call Navy Foam. Then there's a shortcut package for ship hydrodynamics, etc. I'm sure in whatever field you're in, someone made their own release of OpenFOAM specific for that field. One thing I want to point to is this thing called BlueCFD. BlueCFD is basically a containerized version of OpenFOAM that runs in Windows, emulating a Linux environment. So you can, if you're not quite sure, if you want to take the plunge and get a brand new operating system to run OpenFOAM under, you can kind of try it out on a more familiar environment if Windows is your most familiar environment. I should say that BlueCFD, the version of OpenFOAM that running in BlueCFD is considerably slower, using the same hardware as if you were running it native on Linux. In today's course, we're going to be using this one, the OpenFOAM version X. Today we'll use OpenFOAM version 10. The reason we're not using 12 or 11 is that they're not available on ACES yet. So how is OpenFOAM different? I like to use this kind of visual to illustrate it a little bit. If you buy a commercial CFD packet like ANSYS Fluent or Star CCM or what have you, you're buying a kind of a pre-assembled, well-oiled machine. that you can kind of push buttons and change settings to have it do what you want. If you download OpenFOAM, it's not a unit machine that you can run. It's more of like a set of parts and a toolbox for you to assemble to a something that fits your purpose. Now that looks a little bit daunting and scary, maybe, but please remember that there are a lot of already assembled tutorials and assembled case setups online that you can have. So you very, very rarely have to build something completely from scratch. Usually you get something someone else built already, take away a few parts or replace a few parts, and then you have something that's fit for your purpose. So it's more of a little bit of a tinkering rather than building something from scratch. A little bit of pros and cons of OpenFOAM versus commercial packages. Commercial packages, of course, are easier to learn, and when you buy them, you also buy support. Solvers are more stable. I should put this both as, or I think I have put this both as a positive and negative, actually, and I'll let you know why in a second. But commercial packages are typically controlled from a Windows user interface, which is familiar to most people. On the other hand, OpenFOAM is highly customizable. There's no license fee, meaning for a commercial package, you have to pay usually per CPU you're using. For OpenFOAM, it doesn't matter how many CPUs you're using. If you can get your hands on 10,000, it's still free to run it. So it's particularly good for high performance computing. It also has a very active user community, especially in academia. So pre-made setups can be downloaded online, and novel methods typically make it much faster to OpenFOAM compared to commercial solvers. On the negative sides, as I said, commercial solvers are expensive, especially if you need a lot of CPUs. They're not easy to customize. You can customize them, but you have to kind of deal with the company as a kind of an intermediate step. I said that it's a plus that solvers are more stable, but sometimes that is a bad thing, because when you purchase one of these commercial packages, when you spend the money, you expect to get some results out of it, which means that sometimes they've added a little bit too much generosity in having things converging when they probably shouldn't have converged, which doesn't rhyme very well with the kind of garbage in, garbage out philosophy. In commercial packages, you can sometimes have garbage in and pretty pictures out, which can be a little bit dangerous. I prefer it if I've made a bad mesh or a poor setup, that the solver just crashes, because that tells me that something is wrong and whatever comes out of it is not physical. And as I said, novel methods may take some time to make it to commercial packages. On the OpenFOAM side, yes, there's the learning curve for OpenFOAM is much steeper. Solvers are more unforgiving and unstable. I'm not saying that they are unstable. I'm just saying they're more unstable than commercial solvers. But again, I see that as a positive. Sometimes it's frustrating. And to take full advantage of OpenFOAM, you need knowledge of C++ and scripting. I'm not saying you need that knowledge to use it, but to take full advantage of its customizability and the ability to implement new methods, etc., that's definitely something you need. This is a visual overview of the basic structure of when you run an OpenFOAM case. So we have you have OpenFOAM installed somewhere on your system, and that is basically a folder that contains all of these tools and parts that we saw on the previous slides. And then somewhere in your own environment, either in your home directory or if you're on HPC cluster, it's probably in the Scratch directory. You have a folder that contains your particular case. So this folder is called My Case here, but it could be called like Airfoil or whatever it is that you're simulating. This folder contains files, and these files contains settings. For example, there will be files that specify what the solver is, what the turbulence model is, what the convection scheme should be. And when you run OpenFOAM commands in your terminal, OpenFOAM will read these files, and it will pick from this OpenFOAM install location all of these components that it needs to assemble like a working solver. But again, most of this is things that you don't need to change per se. It's just you can change it if you want to. 90% of when you run a case, you just keep it the same as it was in the tutorial, but you change a few key things and you tinker a little bit with it rather than assembling it all from scratch. This is just like a summary of what I said. One thing I want to add is because when you install OpenFOAM, it just puts all of this stuff in a folder. And you can tell OpenFOAM to which folder it should look for all the components and tools in, which means you can have as many versions as you want installed at the same time. You just need to make sure that when you open a terminal that you point to the one that you want, the version that you want. And if you're using your own system, you're probably using the bash rc file in your home directory. If you are on ACES or any other cluster, you're probably using module load. Just so you are aware of, you don't need to stick to one version of OpenFOAM. You can keep as many as you like because they may all serve slightly different purposes for you. And case files are stored in your user profile, either in home, or if you're on HPC, it should be Scratch. So what's inside that folder? In this case, it's called my case, but again, it could be called like airfoil or whatever it is you're simulating. Inside every OpenFOAM case folder is 3 main folders, subfolders that are almost always present. There's one called system, which contains files that control the simulation, the solver, etc. These are usually runtime modifiable. So while the simulation is running, you can go in and change something in a file, and it will just change it in the simulation as it goes. So this contains like start time, end time, time step, settings for the solver, numerical schemes, and mesh refinement settings. The constant folder contains, unsurprisingly, things that are constant, like physical properties, environmental constants, turbulence model. The mesh is here too. Mesh is not always constant, but in the initial stage of the simulation, the mesh is seen as a constant. If the mesh changes at some point along the way, that will be saved in the new folder. Then we have 0, which is a time step folder. 0 is always there, but when you start running the simulation, so for example, when you get to iteration 1 and you want to save the data there, you will get a folder here in the same directory called 1. Then you will get another folder called 2, 3, 4, 5, 6, etc. And this contains basically the raw data of what the fields are, like the velocity and pressure fields, or turbulence intensity, or whatever it is. The reason that it's here already before we started the simulation is that these folders contain the boundary and initial conditions. So initial conditions that's why it's called 0. That's what it is at iteration 0. But the boundary conditions are also found inside these files in the 0 folder. All tutorials in OpenFOAM, there are so many tutorials. There are slightly different tutorials for each development track, like the OpenFOAM Foundation one, or the CFD Online, or sorry, the OpenCFD one. So before you decide which one to go for, have a look at which tutorials they contain. They may contain a tutorial that's very similar to what you want to do. All tutorials contain an all-run script, and basically that's a script that runs all the commands that you need to run in order. You just have to run that script to complete the tutorial. But that's a little bit cheating. It's not, we don't learn a lot from that. So in this section, in the hands-on section, we'll go over them manually and discuss what they do. But the all-run script is still useful, because if you download a tutorial, or if you use one of the tutorials that are in your version of OpenFOAM, you can open the all-run script and see what commands are involved in running this tutorial. So it gives you an idea of kind of what tools are being used. So in essence, to run an OpenFOAM case, we changed our working directory to a case file. That's that folder, sorry. That's the folder that contains the zero, constant, and system subfolders. Then we type the name of a command. We can look at the all-run script to get clues what commands need to be run for this particular tutorial. And when you run those commands, OpenFOAM will read all the settings files in the system, constant, and zero folders, and it will run. So that concludes the intro. So we're going to go ahead and go to the hands-on session. So I'm going to stop sharing here and share something else. And I think the course material, the link to the course material was posted in the chat. So if you want to go ahead and download the file that is called instructions, that way you can follow along with what I'm doing, and more importantly, you can also copy paste commands and text from that file, so you don't have to type everything out. But I'm gonna show you how to get to that file, because you might want to go back to it later after we close this Zoom session. So now I am at the HPRC website, hprc.tamu.edu. And if you look under training, courses, scroll down a little bit, we have Introduction to OpenFOAM here. If I click View Details, this is where you can find the instructions. So the slides that I just went through are here. And then the instructions document is here. And the instructions document looks like this. So again, I want to stress this, you don't need me in order to complete this course. I'm going to do exactly what it says in this instructions document. So if you want to do it by yourself, if you lose me at some point, or just want to go back and try something again, you please use this document, and that website will stay up even after this course is complete. So the first step is we're going to be logging into ACES. And again, I'm at the HPRC website, hprc.tamu.edu. We go to the portal, ACES portal. Now, this will look slightly different depending on your institution, but I'm going to select Texas A&M University here, and it's going to send me to my my SSO login. Hopefully I typed password correctly, looks like it. Okay, if you see the ACES logo, then we have success. So I'm going to pause for a second here, or a minute, to make sure that everybody are able to log in. If you're not able to log in, please post in the chat. So I'm going to pause for a little while just to make sure that everybody can log in. I don't know, last time we were able to create a poll or something to just check that everybody has been able to log in. But if you haven't, if you're having any problems to log in, just please post it in the chat. We can see if we can figure it out. I didn't see anyone posting any issues. So I'm gonna slowly continue. Before I continue, I can show this one. If you click on the dashboard, you can see the current status of the cluster. So we can see that there are quite a few cores available. For this course, we made a reservation, so we don't need to wait in line, wait in the queue, which is fortunate. Okay, so I'm gonna start the hands-on session. So as I said before, OpenFOAM is entirely text-based. So we don't really need any graphical user interface for it. So normally, if I'm running OpenFOAM on the cluster, I usually just use the shell access, which means I can type commands and I can modify files, text files. However, today I wanna incorporate ParaView in this course as well. ParaView we use for visualization and post-processing. And in order so that we can run both OpenFOAM and ParaView together on ACES, I'm going to be using a VNC. So that's like a virtual desktop that gives us like a graphical. OpenFOAM still doesn't have a graphical interface, but at least we have like a graphical desktop that we can work with, and we can show ParaView in. And there should be a button here that says VNC OpenFOAM short course. If you're doing this not during this course, you would just click this normal VNC. The only difference here is if you click this one, you should have a spot reserved on the cluster, so we don't have to queue. So I'm going to go ahead and click this one. And this is where you select what resources you're requesting. So we are requesting CPUs only. I'm going to put it to 3 hours. I know we only have like 2 hours left, but just in case, I'm asking for 3 hours. I'm going to be asking for 3 cores, just so we can do a little bit of parallel processing towards the end. And I'm going to be asking for 5 gigabytes. And I believe these numbers are also given in the instructions documents if you get to this point and have forgotten about them. And I'm going to click launch. Hopefully it shouldn't queue for too long. It shouldn't be queuing at all, but we'll see. Here we go. Now it's running. Then I can click launch VNC. Okay. So now I have a kind of a virtual desktop here. I'm logged into a compute node, AC014 on ACES. The first thing I want to do is it came up with a terminal here, but I'm going to minimize this terminal because this terminal is what controls the session. So if I accidentally close it or something happens with it, it's going to close the session. So I'm going to minimize it, and I'm going to right click and I'm going to click Xterm, which opens a new terminal. So this is the one we're going to be running OpenFOAM in, and I'm going to see if I can increase the font here, font size, so you can see. So now we have a terminal that we can run OpenFOAM in. So the first thing I want to do is, for this course, I prepared a few scripts that makes life easier. It means I don't have to type so much. And if you log into ACES at some later point, these scripts should still be available. But if you're on another system, these scripts won't be available. But in the instructions document, I put both the commands that you type if you have these scripts and the commands that you type if you don't have these scripts. So don't worry. So I'm gonna do source, Scratch, training, OpenFOAM, OpenFOAM functions. Now, that was a little bit quick. If you're unfamiliar with Unix environment, if you start typing something and hit tab, it's gonna fill in automatically if there's only one thing that exists with the thing you typed. So I don't have to type everything manually. So if I do this, I should have some commands available. The first thing I want to do is I want to load the modules for OpenFOAM. There are a bunch of modules. Again, in the instructions document, you can see what they are. But here I boiled it down to just this command, load OpenFOAM 10. That's going to take a little while to do, I think. Okay. There's a little error there. I'm not sure what it is, but it doesn't seem to affect anything. So I would say don't worry about it. The next thing we want to do is we want to create a folder where we put our OpenFOAM cases. So I will do that in Scratch. And I will call it not foam run, foam run. And then I will change directory to that directory. Right now that directory is empty. The next thing I want to do, so now I'm set up in this terminal here. I have loaded OpenFOAM. I have created a directory where I can run where I can put my OpenFOAM cases. So I'm pretty much ready to go. I want to open another terminal now where we're going to run ParaView in. Normally, on most systems, you can run ParaView in the same terminal, but on ACES, for some reason, there is some conflict between loading the ParaView and OpenFOAM modules. So I'm going to load the ParaView module in a separate terminal. So again, in this terminal, I need to source that that training script file. So I'm going to do this, Scratch, training, OpenFOAM functions, and then load ParaView 11. Okay, so in this terminal here, I have now loaded ParaView, and ParaView is ready to use. So, but we don't need ParaView right now, so I'm just going to put that to the side for now. The next thing we want to do is, as I mentioned during the intro, OpenFOAM has a big pile of parts and tools that you have to assemble yourself. Fortunately, you don't have to assemble it yourself because there are already so many pre-assembled tutorials. So for me, when I've been using OpenFOAM, I have always started with a tutorial and then modified that tutorial to suit my needs. That's basically the process that everybody follows. So you can look around in tutorials again for the different versions, find one that's similar to what you want to do. And I should say that geometry, meaning whatever the object is that you're studying the flow around, that's fairly easy to change, but the main setup of the flow solvers and stuff like that are things that are maybe slightly more difficult to change. So if you find something that has the same geometry, if the setup of the flow solvers doesn't really match what you want to do, that's not really bingo. But if you find something that does the same kind of simulation that you want to do, but has a slightly different object or a different object that it's calculating the flow around, that's pretty good because the geometry you can change more easily. Okay, so I want to copy one of the tutorial cases, and I made a script called copy foam tutorial. This is from available on ACES, but it's not available on your system probably. But again, I put all the commands that are behind this command in the instructions document. And today we're gonna do a tutorial called Wind Around Buildings. I'm not an expert on building aerodynamics by any means. The only reason I picked Wind Around Buildings is that it's simple. It contains most of the basic commands that you need to run when you run a case without a lot of other stuff around it that we need to worry about. So if you are not into building aerodynamics, don't worry. This is all applicable. Most of this is applicable to any OpenFOAM case. It's just that there are slight variations for each case, and this one is a simple one that we can run for this course. So the next thing we're gonna do is we're gonna go to this folder that I created called Wind Around Buildings. And now, as I said, it contains these three folders: 0, constant, and system. It also contains the allrun script. If I just run this allrun script, we will have completed the tutorial, but we're not going to do that. We're going to do it step by step. So I want to just quickly look at some of what's inside some of these files. We're not going to touch them at this point, but I just want to show you what's inside, that there's no magic going on. So if we, for example, look at a file in the system folder called FV solution, you don't need to open these if you don't want to and play around for yourself. I'm just opening them to show you what they contain. So the FV solution contains settings for the matrix solvers. So for example, for P, we have a generic algebraic multigrid solver with a Gauss-Seidel smoother and has a certain tolerance. For all the other variables, we have a solver that OpenFOAM calls smooth solver with another type of smoother. We're going to be using the simple algorithm for pressure velocity coupling, so you can control it here. We see that we're not doing any non-orthogonal corrector steps in the simple algorithm, but if we have problems with convergence, then we might consider that. Residual control is an important thing. That means that if the residuals go below the values that you specify here, the simulation will stop automatically. If they never go below these, it will just continue until whatever stop time, end time you specify. And we're going to look where we specify that later. Then we're not doing anything with potential flow in this tutorial, but it's still there. The settings for it, and then we can specify relaxation factors on all the fields. So that was the solution, FV solution. Then there's another one called FV schemes. FV schemes contains numerical schemes. So for example, for time derivatives, there aren't any. We're doing a steady state simulation. For gradient schemes, we're using linear gradient. For divergence or convection schemes, we're using a linear upwind. For the turbulence quantities K and epsilon, we're using limited linear, which is a TVD scheme. So it's a mix between upwind and central differencing. I don't think we have anything with Laplacian here in this solver, but for example, if you're running some kind of post-processing utility that uses streamlines or any other kind of like Laplacian calculations, then it would look for what scheme to use here. That's about it. Then we're gonna look at a dictionary called ControlDict. ControlDict is the kind of highest level dictionary in an OpenFOAM case. It contains things like start time, end time, delta t. Now this is a RANS simulation, so there's no time stepping. So delta t here doesn't really mean anything. It's just one. It tells OpenFOAM how often to write everything, the fields to a file, and a lot of other things. And then we're gonna look at, for example.
Hey, Bjorn.
Yes.
We have a question in the chat.
Yeah.
Yeah.
Hang on. Let me see if I can open it. Oh, to get a second terminal, just right-click on the desktop on the background and click Xterm. Hopefully that works. Next, we're gonna look in the 0 folder, which contains. Actually, I'll just change to the 0 folder so you can see what it contains. It contains all the fields that we're solving for in this simulation, one file for each. So epsilon, k, nu t, p, and u. And this will be the initial and boundary conditions for these fields. I'm going to have a look at the one called u. That's velocity. So there we can see we have a boundary field, which is the boundary condition. At the inlet, we have a fixed value uniform over the entire patch. And the value is u inlet, and u inlet is defined up here as 10 meters per second in the x direction. Outlet, we have an adapted boundary condition called pressure inlet outlet velocity, which is basically a condition that changes between an inlet and an outlet based on the direction of the flux, so that we don't get any propagating effects from that boundary condition into the domain. The flow should just pass through it. And then we have a wall that has a no slip condition. And all the other files look similar to this. Obviously, they have slightly different boundary conditions. One thing I should mention here, OpenFOAM sometimes has funny names for its boundary conditions and numerical schemes and what have you that are specified here in the files. This one is fairly descriptive, pressure inlet outlet velocity. But if you want to know for your specific setup and your specific solver, what are boundary conditions or turbulence models or numerical schemes or whatever it is that you're setting in these files, what options do I have that are compatible with this particular simulation? And the trick that I learned a long time ago is I delete this and then I just type some gibberish instead of it. Because what's going to happen is if I run the simulation now, OpenFOAM is going to complain that it doesn't know what this gibberish boundary condition is. So it's going to say, I don't know what this is, but here are all the boundary conditions that are compatible with this simulation. Again, that's going to still mean you have a lot of funny names maybe, but then at least you can kind of Google them and see what they do, or you can go into the source code and look for yourself what they do. One thing I want to mention more with this U file. When you look in OpenFOAM files, you will often see this either like this, dimensions and then a vector, or if sometimes it's given as a constant, for example, say viscosity, and then there's a number and then this vector. And this vector is OpenFOAM's way of keeping track of dimensionality. So OpenFOAM makes sure that the dimensions are correct for all the equations that you're solving. And each element of this vector is some SI unit. So from this one, we can guess that the second one is probably length, and the third one is probably time. So meters per second is the dimension of velocity. So that's what this means. If you see this somewhere in the code, or if it complains that 0, 1 minus 1 is not equal to 0, 1, 1, that means that there's something wrong with the dimensions that you specified. Okay. So I think that's about it. I'm not going to go into the constant folder in the interest of time. It's mainly just some numerical constants that are specified, like, or physical constants like viscosity and density and stuff like that. Instead, we're going to go, I'm going to just quickly reveal what's inside the all-run script. So it's a few commands: surface feature, block mesh, snappy hex mesh. When it says like this, get application, then it will get the application name from the control dict. And the application name in the control dict was SimpleFoam, which is the solver that we're going to be using. So we're going to run these in order. We're not going to run this surface features because for some reason it's broken on ACES, but it's not necessary to run this tutorial. So we're just going to skip it, and we're going to run block mesh. And I'm going to quickly show block mesh is OpenFOAM's basic meshing tool. It creates meshes in blocks, as the name suggests. And we use it as a background mesh generator for OpenFOAM's unstructured generic geometry mesher called snappy hex mesh. And I'm going to stop sharing this for 1 second, and I'm going to share instead my slides, because this is a little bit difficult to explain with words. It's easier to do visually. So when we mesh in OpenFOAM, we use snappy hex mesh. Snappy hex mesh is a parallelized automatic quality control automatic meshing tool that usually works on STL CAD surfaces, but there are some other CAD surfaces where it's compatible with too. I put a link here in the slides. There's a comprehensive guide to snappy hex mesh if you want to learn more about it. But basically, it has a few key steps. The first step is to have a uniform background mesh, which is this gray block here, which we use block mesh to generate. The next thing it does, it detects where the CAD surface is, and it starts splitting the cells to refine on that surface. Then it determines, or you have to pick if you want the mesh inside the CAD surface or outside. So you pick an inside or outside point, and then it will remove whatever is inside or outside, depending on what you choose. And the final step is that it snaps the mesh to the surface. Then there's a step after this where it can grow prism layers out from the surface to resolve boundary layers, but that's not part of this tutorial. So when we run first block mesh and then snappy hex mesh, this is what we're doing. We're using block mesh to generate this uniform gray mesh behind it, and then we use snappy hex mesh to start splitting the cells and snapping them to the surface. So I'm going to go back to my terminal. Here we go. I'm going to look at the file called block mesh dict, which controls the block mesh utility. So it contains some vertices, basically 8 points. One block has 8 points, one cube or hexahedra. And then we form a block out of these 8 points. If you want to know what order to put the points in, there is a good guide in the OpenFOAM user guide. But this is a tutorial, so they've already figured it out for us. This is very simple. It's just one uniform block, and it spans these dimensions that we've set here. In block mesh, we also define on the block what are the patches on the block. So we have an inlet patch, an outlet patch. We have a ground patch and a front and back patch. We don't have a patch for our buildings. Remember, we're doing a wind around buildings because that's not generated by block mesh. That will be generated by Snappy Hex Mesh later. So I'm going to run block mesh by typing block mesh. Again, this reads that file, and it also reads the control dict, and we'll run the block mesh utility. That was very quick. So we can see it generated 6,000 points, 5,000 cells, 16,000 faces. So now we have a mesh, but it's just an empty domain at the moment. It's just a uniform mesh. So we're going to run Snappy Hex Mesh. Before we do, I just want to show you the file that controls Snappy Hex Mesh, which is in the systems folder, Snappy Hex Mesh dict. It looks like this. First, we have a few switches. So it has three phases: Snappy Hex Mesh, Castellated Mesh, Snap, and Add Layers. And these are the three phases that I showed on that little graphic, where first we refine on the surface and cut away the inside. Then we snap to the surface, and then we add layers. But add layers is off here because that's not part of this. Next, we have some geometry. So we have a CAD file of our buildings called buildings.obj. And then we have a box that we want to refine inside. So again, the geometry part of this dictionary doesn't say anything about the mesh. We're just defining some geometry. We have some buildings here, and then we have a box. This is Snappy Hex Mesh has a function to refine on features such as sharp corners and stuff like that, to add extra refinement to resolve those. But that's the functionality that's for some reason broken on ACES. So we're not going to be using that. Then we have refinement surfaces. So these are surfaces where we refine on the intersection between the background mesh and a CAD surface. This one we're going to do on the one we call buildings. And this buildings is what we called it in geometry. So you define the geometry here, and then when you define the refinement, you say what part of the geometry you want to refine based on. So refinement surfaces refines only on the surface. Then we have refinement regions where it refines everything inside a specific region. And we say we want to refine everything inside this box that we set. And again, here we have inside point. Again, you have to, Snappy Hex Mesh has to know if you're interested in the mesh inside the CAD file or outside the CAD file. And then we have a few more controls that we're not going to touch here, but that's the essence of it. So if I try to run the Snappy Hex Mesh now, it's not going to work because you saw that I had that feature, snapping to features option active, and that's broken, so it's going to crash it. So I made a script which is called disable SF_10, which means disable surface features for OpenFOAM 10. But again, in the instructions document, it says what commands you need to, or what you need to do in order to do that manually. But I'm going to do it now, then it should work. So now I'm going to run Snappy Hex Mesh. I'm going to run it with an overwrite flag. If I don't use the overwrite flag, Snappy Hex Mesh is going to save for each step, like the castellated mesh or the refinement phase and the snap phase. It's going to save the mesh to a new time step. So it's going to create time steps 1 and 2. But we don't need that. We'll just overwrite the mesh that is in 0, so we can start our simulation from 0. So hopefully this will work. It's going to take not too long, but I have time to answer a question or two while it runs, and then it flashes by pretty quickly, but we can scroll back up a little bit and see what it does once it finishes. It shouldn't take too long. Okay. I don't see any more questions popping up, but let me know if some pop up later. So it finished. I want to mention, we see here there are a lot of zeros here popping up. We love to see those because I mentioned it very quickly before, but Snappy Hex Mesh is kind of unique in that it does quality control as it's refining. So in each step or each iteration where it refines and snaps the mesh, it checks that the quality of the mesh is good. And if the quality of the mesh isn't good, it will try to adapt to keep these constraints. So non-orthogonality less than 65 degrees, etc. And you can change. This is kind of sometimes restrictive because it will mean that it just doesn't refine certain things if you're too like strict with these requirements, but you can relax them and you can do what you want with them. But it's really nice to have something that keeps track of this as it does the meshing. There's not much more I can say about the terminal output here. What I can say, if you don't want to scroll in a Linux environment, if you write the same command I just did, right arrow, and then write a file name, it will, instead of like vomiting it out in the terminal, it will put it in a file instead, so you can scroll through it later and have a look at what it did. But I put it out in the terminal now just so you can see what's going on. Okay, so we have a mesh. Let me see, it says, I think we have 185,000 cells, so a bit more than the 5,000 we had in just the background. That means we have refined around those buildings, and we're going to see what they look like a little bit later when we look in ParaView. So next we are ready to run the solver, and the solver is SimpleFoam.
Beyond?
Yes.
You have some questions in the chat.
Okay. Let me give me a second. Okay, so I did not load another source file. I did the, were you able to run, the question is, if you don't have a snappy hex mesh command, what's wrong? Well, first of all, I don't know if that's just a typo, but there are no spaces in snappy hex mesh. But if you were able to run the load OF10 command without errors, then the snappy hex mesh should be loaded. There, I haven't run any other commands to load anything. Okay, just check 1 second that I didn't miss anything. No, I don't think I did. No. Okay, so we're ready to run the solver, which is SimpleFoam. So I will just type SimpleFoam and hit go, and it's going to run. And as I said before, it's going to run either until the residuals for pressure and velocity and turbulence quantities satisfy those criteria that we specified in FV solution, or until it hits the end time, which we specified in control dict, which was 400. And I did this before, so I know that it's never going to satisfy those criteria, so it's just going to run until 400. So I have time to take more questions. So were you able to run Snappy Hex Mesh now? Yes, if you're getting that error, cannot open buildings.emesh, then you have to run the disable SF10 command, because that means that it's trying to do the surface features, which is broken. So if you run the disable SF, I think I forgot what it was. Let me check what it was, except disable SF_10, then you should not be getting that fatal error. And block mesh is block mesh with a capital M. That's probably why it doesn't work, if it doesn't work. And again, if you don't keep up with all the commands, I know I'm typing a lot of things and a lot of commands and a lot of file names and stuff, but if you have that instructions document, all of the commands that I'm typing are in that document, so you can look at it later, or you can copy them over in your own time. But I'm gonna try to I'm trying to go a little bit quick so we have time to show everything, but I'm happy to stop every now and then and check that that everyone's on board, especially now since we're waiting. And the same thing I said with Snappy Hex Mesh, if you don't want, so normally if you submit OpenFOAM commands as a job to the cluster, you don't want it to just dump it to the regular output like this. You will probably want to save it to a file. So if you do that right arrow simplefoam.log after the simplefoam command, it will save it to a file. Then you can kind of keep track of what it was doing. So it should be finishing in a few seconds. Okay, we hit the 400. So I was correct that we never satisfied the residual criteria for all the quantities. It looks like the major culprit was P here. The residual is 10 to the minus 3, and we said it has to be 10 to the minus 4 for the simulation to stop automatically. So that we completed the wind around buildings tutorial. What we're going to do now is we're going to look at what we did because all we've seen so far are black and white numbers, which isn't very interesting. Fortunately, we have ParaView. So I prepared. Did I prepare something before? Yeah, I think I prepared a terminal before. Yes, we had this terminal. If you remember, all I did in this terminal so far is I sourced this script of OpenFOAM functions, and then I loaded ParaView 11. So now I want to go to that wind around buildings folder. So I went to scratch /foam run/wind around buildings. And we can see that now this folder contains, it used to contain only 0 constant and system. Now it contains 0, 50, 100, 150, etc. So it contains every 50 time steps it's saved, which it did because we told it to in the control dict save every 50 time steps. Now there are a few different ways to load this case into ParaView, and I put those in normally if you have OpenFOAM loaded in the same terminal as ParaView, you can run a script called parafoam, but now we have them in different terminals, so we have to load it manually. But I prepared a script called pv11 load case, which will load whatever case you're in the folder for into ParaView 11. So I'm going to do that. It's giving a few errors, but as long as it launches, it's fine. Now I'm going to see if I can reboot it a little bit, because it's sometimes trying to why it open in full screen like that. No. I'm going to close it again if I can. Okay, I don't seem to be able to close it. Never mind. I can see what I need to see. So we have loaded this case into ParaView. You can see up here on the top left or the far left that we've loaded wind around buildings. ParaView is like a pipeline kind of software. So you apply things gradually, and you can apply filters. You can apply filters to filters, etc. So we always start with this wind around buildings route. That's the entire case, and then we can sort of pick out what we want to visualize. The first thing I want to do is I want to select down here the buildings, because otherwise we won't be able to look at those. We won't be able to isolate those and look at the buildings. And then I'm going to hit apply. So this is what it now looks like. In order to view the buildings, I click on filters. I click on alphabetical. There are a lot of filters. I'm going to pick the one called extract block. And then here I'm going to select buildings. This means that I'm visually removing everything that isn't the building patch. I'm not removing it from ParaView. It's still loaded. It's just that, again, we're in a pipeline kind of browser here. So what I've done is I've applied a filter to wind around buildings, the root here, which is to extract only the surface of the buildings. So anything I do when I select this one, I will do only to that surface. If I click the root again and apply some filter, I'm going to apply it to everything. But if you have the block selected, you're only going to apply it to the block. So this is what it looks like. These are the buildings that came with the tutorial. I don't know if anyone knows what city it is. I don't. But we can see the wind is coming here from the left, and we got high pressure on this building here because it's exposed, and it's kind of lower pressure on the other buildings. This is now showing iteration 50. I want to be showing the final result, so iteration 400. It didn't make a huge amount of difference, but that's the final result. If you click these controls up here, you can do animations and you can step in time, but this is RANS, so we always want to look at the final result. Okay, so that's pressure. We also want to look at velocity, where the velocity is high, and we want to do that. We want to look from above, maybe like that. No, that's above. And again, now we have this extract block selected, which means if I try to make like a visualization of velocity here, I will only see velocity on the surface of these buildings, which according to the boundary conditions, it's 0. So that's not very interesting. So if I want to visualize velocity, I want to again click the root of the pipeline so that I apply my filter to everything. And the filter I'm going to be using is a slice. I'm going to make a slice and I want to make it the normal. And then I want to show the slice at 30 meters above the ground. And then I hit apply. And this is now we got the slice selected. The slice is now colored by pressure, which is not what we wanted. We wanted it to be colored by velocity. So there we go. This is the velocity. You can see again, the wind is coming from the left here and is creating a wake and some turbulence here behind a bunch of the buildings. And that's the end of the first part of this course. We've successfully ran the tutorial to its completion. And I think we may want to have like a short 5-minute break before we continue with the rest. I'm going to resume in a minute or so. I just wanted to address, there was a comment that I just wanted to clarify that the instructions for the tutorial where you can copy all the commands and stuff is not the same document as the slides. There should be 2 documents on the course website, one called slides and one called instructions. I just wanted to make that clear in case anyone got confused. Go back to sharing my screen. Okay. So we successfully ran a tutorial, the wind around buildings tutorial. But that's not very useful if you're not interested in wind around buildings, which again, I'm not a building aerodynamicist. I just picked this one because it lent itself well for demonstration. But if you wanted to do something that isn't readily available, if you're lucky enough that whatever you want to do, there's a tutorial for doing exactly that, congratulations, but there probably isn't. But I want to show that it's fairly easy in OpenFOAM to modify it to do what you want. And what we want to do with this wind around buildings is we want to put in a new building, and we want to see, you know, how the aerodynamics around the other buildings affect the forces and moments on a new building, because that's probably something that someone might be asked to do if they're an architect or a civil engineer, to figure out what the wind loads are going to be on a particular building. So we are going to go back to this foam run directory. This currently only contains the wind around buildings folder. But we're going to create, I'm not going to overwrite the wind around buildings. Instead, I'm going to make a new copy. I'm going to copy the exact same tutorial, wind around buildings. So at the start, it's going to be exactly the same as the one we just did. But I'm going to call it wind around, what did I call it? Wind around new building. Okay, so now we have 2 folders, wind around buildings, which was the case we just ran, and wind around new building, which is the one we're going to be working on. So I'm going to change to the wind around new building folder. Again, it looks the same as it did before, 0, constant, and system. But now we want to start adding things to this. So we want to start by adding the building itself, and we do that in the snappy hex mesh dict because that's where the geometry is defined. So and this is where you really need the the instructions document if you want to keep up, because I'm going to add in quite a lot of stuff here that I don't want to type. I'm going to see if I am able to copy it. So this is the instructions document. And we are here. So in geometry, I'm going to add all of this and hope that it works. It doesn't. It might be that I haven't. There we go. Okay, so if you have problems copying and pasting, for me, Control V didn't work. It worked like an hour ago. I'm not sure why that didn't work now, but Shift Insert worked. And I should also mention that I'm in Google Chrome. And when I started this up in Google Chrome, it asked me for permission to access my clipboard, which meant I can just paste directly into the VNC. If you are on any other browser, like I tried Firefox before and it didn't work. If you're on a browser that where you can't, where either Shift Insert or Control V or whatever command you use on your system to paste doesn't work, there is a little clipboard. If you click at the far left here, there's a little menu, and there is a little button here called Clipboard, which contains my clipboard. And now you can see I have that stuff in my clipboard already. But if you didn't, if the copy paste didn't work, you should be able to paste into here instead of into the actual terminal. So you can paste into here, which will put it on the clipboard of the VNC session, and then you should be able to use Shift Insert or Control V or whatever. Shift Insert should work for most systems. That's the one that just worked for me. Anyway, in geometry, you can see I pasted this. So we still have our original buildings here, but I'm adding a new building. And OpenFOAM has ways to create like basic geometric shapes. This one is called searchable cylinder, which is basically a cylinder, which is defined by 2 points. So we have X, Y, and Z, and the X and Y are the same. So we have a so these are the endpoints of the cylinder, basically. So the X and Y are the same. So we have a line that goes straight up and goes from 0, which is ground level, to 225 meters. And it's got a radius of 25 meters. So that's our building. It's a cylinder, 225 meters tall, radius of 25 meters. Then I need to tell it to refine on this new building. So I'm going to copy that. And in refinement surfaces, I'm going to add new building, or Control V work now for some reason. But Shift Insert works as well. So I'm going to tidy it up here a little bit so it's easier to see. So we see we have buildings refined to level 3. The reason that there's 2 here is you can have like there's a little bit of play in that you can specify a minimum and maximum refinement level, and it will, it will try to control the quality. And if it doesn't like the quality, it can reduce the refinement level or increase the refinement level at will. But by putting 3, 3 here, we're forcing it to be 3 at all times. And then patch info is wall, meaning that it's going to create a new boundary condition called new building with a patch boundary condition type wall. So that's it. So now that's basically all we needed to do in order to add the new building into the geometry and refine around it to incorporate it into the mesh. One thing we need to change, I'm going to save this and I'm going to go to block mesh dict, the building in question was 225 meters tall, but the background mesh we created here was only 140 meters tall. So that's going to be a problem. It's going to stick out of the domain. So I'm going to put this up to 300. Okay. Now that should be it for the simulation, but we want to get some kind of data out of this other than just looking at pictures. And the data I wanted to get out of this is to measure the force and moment on this new building. And we do that in control dict. We open the control dict for editing. Make it a little bit bigger. Okay, at the bottom here, we have something called functions. This is really useful. OpenFOAM has a lot of functions that it can run during runtime. Things that keep track of things that, for example, calculate forces on objects, things that can start and stop the simulation automatically, things that can write files or delete files or create files automatically as the simulation is running, based on whatever conditions you specify. But we're going to use it here to calculate the forces and moments on the new building. So I'm going to again copy all of this from the instructions, and I'm going to paste it here. Oops, that didn't work. That still didn't work. Maybe I didn't copy it properly. Copy. Oh, okay. I'm going to do the clipboard thing instead. Doesn't seem like it has copied. Okay, there we go. Okay. So I was able to copy this. It's not usually this fiddly to copy and paste things for OpenFOAM. It's just because we're running this VNC session, so I can run ParaView at the same time. If you're not in this course, I would recommend maybe running OpenFOAM separately in a terminal and then running ParaView somewhere else, just because it makes it a little bit easier. But anyway, we pasted this here. So we're saying this is what I called it, force coefficients 1. That's just the name I gave it. Force coefs is the name of the function. You have to tell it which library this function can be found in. And then we say that we will write the forces based on the time step, and the time interval is 1, meaning every time step. And then we want to calculate forces on the new building. And then we specify like which direction is lift and which direction is drag. We specify what the center of rotation is, which, if you remember when we created this building, this is the base of the tower. And then we specify which axis is pitch. And then this is for non-dimensionalization, what the magnitude of U infinity is. And then this is a characteristic length also for non-dimensionalization, which is 50. That's the diameter of the tower. And reference area is the projected front area of the tower. Okay, so that's done. Let me see. So now we're ready to go. So we run the same things that we did before. I'm going to run it more quickly this time because we don't need to talk about them. But first we run block mesh to create the background mesh. The background mesh is now slightly bigger because I raised it to 300 meters. It has the same number of cells because it just stretches it out, but that's fine. And then we're gonna do the disable trick. because otherwise Snappy Hex Mesh will throw an error. As some people noticed, I will disable the surface features so we don't snap to, we don't do any particular refinement or snapping to sharp edges. And then we're gonna run Snappy Hex Mesh over right. Okay. So this shouldn't take too long. Again, we see a lot of zeros flashing by. I saw a 4 there sometimes, so there it did a few more iterations just to get rid of some bad quality cells. Okay, so we're done. We got a mesh, including the new building. So then we're gonna run SimpleFOAM. And now you can see, because I put that force coefficients function in every time step, it's throwing out the force coefficients, but we don't need to read this. We just, it's saving it to a file as well. So it's just reassuring to see that it's doing it, but we don't need to read what it does. Okay, yeah, this is gonna take a little while, so let me know if you have any questions so far. Okay, we're about to complete the simulation. Again, it ran to 400 seconds. I want to show that in a folder called post-processing, it saves the output from this force coefficients function. So I can just show for each time step, it output the XYZ force. Oh, sorry, no, I think it's the coefficient of lift, drag, radial force, and moment. I don't remember exactly what I told it to output. But this doesn't tell us a lot. If you're just want to do an analysis and get a number, this is RADS, so you can get the final number is the converged value. But we might want to look at a little bit about either if you have an unsteady simulation or if you want to look a little bit what the convergence looked like, we can plot this, and we're going to plot it using NuPlot, which is on ACES and was on pretty much every Linux system. And using NuPlot, we can plot directly the columns of this file. Let's see if I can paste that here. I can't. Can I paste with Shift Insert? Yes, I can. Okay. So I pasted that command from the instructions document. So I plotted this file using column 1 versus column 2. I think that's the drag coefficient on the building. If I'm not mistaken, it's either the drag coefficient or the moment coefficient. I don't remember which one is which column. But in either case, you can see for the first 50 iterations, it kind of went a bit crazy and then it stabilized. And this tells me that this requirement that we had, that the simulation needs to get to a residual of 10 to the -4 before it stops, is maybe a little bit too strict, because we could have stopped it here and gotten the same, could have stopped it at like 75 iterations and still gotten the exact same answer out. So that's using NuPlot is an excellent way to kind of visualize these things very quickly, but also for generating figures for reports and stuff. NuPlot is a pretty powerful tool. So that's what we got. I'm going to close NuPlot. And the next thing we want to do is we want to look at this in ParaView. And if you remember, I'm going to do that in a separate terminal. I'm going to make sure that I have the right terminal. Yeah, it's this one where we have ParaView loaded. And then I'm going to go to this wind around new building folder. And again, run this PV11 load case script. Okay. And now I've got both the buildings and the new building here to load. I'm loading these just so we can we can separate them out. So I'm gonna select those two and the internal mesh and load the entire case. And you can see that the domain is considerably higher now. We're gonna do again, oops. We're gonna do the extract block, and we're gonna extract both the buildings and the new building. And there we go. So you can see that we made quite an obnoxious addition to this city in terms of this huge cylindrical tower that we have now calculated the forces and moments on, and we can see that it's kind of in the wake of some of the other buildings here, but it's very exposed up here because it's so much taller than everything else. So that was the end of this part of the tutorial, how to modify a tutorial to suit your needs. Obviously, usually it's a little bit more difficult than just adding a cylinder to existing tutorial, but I think you get the idea that there are a few key files that you need to go in and change to suit your needs. But there's no magic going on. I just went in and added a cylinder, extended the domain a little bit, and put a function in to keep track of the forces and moments. So that's it. Okay, so the next thing we want to do is we want to run this thing in parallel, because we are on a high performance cluster. So we should take advantage of the fact that we can scale this using more CPUs. We've been running it on one CPU up until now. So I'm gonna go to the original wind around buildings case. I'm not gonna touch the wind around new building one. I'm gonna clear the screen so it's not so messy. In order to get the case ready for parallelization, we need another dictionary. And this tutorial, it was meant to run on only one CPU, so this tutorial doesn't have this dictionary. So I'm gonna steal it from another case. But again, I made a little script to do that, which I called get DCPD, which stands for decompose par dict. Decompose par is the OpenFOAM's utility for decomposing the mesh into different processors. So I'm gonna run this little function that I made called get DCPD. Now we should have a file called decompose par dict. So I'm gonna open it. It's in system, decompose par dict. This is another dictionary that controls, as I said, how the domain is being decomposed. And you can do various ways of decomposing it: simple, hierarchical, Scotch, whatever you want. In this case, if you remember, we requested 3 cores. So we have 3 cores available here, which means I want to change the number of subdomains here to 3. And in hierarchical coefficients, the multiple of these numbers should equal the number of subdomains. So I'll just change this to 311. 3 times 1 times 1 is 3. So this should decompose it in 3 subdomains, mainly aligned along the x-axis based on this hierarchy here. Okay. The next thing we want to do is I want to remove all the old time step folders, because otherwise it's going to decompose all of them too. And we don't need that. So I'm gonna I'm gonna do that. And now you can see that we're left with only the 0 constant and system folders again. So now I'm going to run decompose par. So you can see here it created 3 processors, 0, 1, and 2, with about 60,000 cells in each one. I heard that there's a good practice if you want ideal efficiency to keep it around 50,000 cells per processor in OpenFOAM. Of course, you can add more processors, but in the eventually the intra-processor communication is going to take up more time than the actual calculation. So we want to try to keep it around 50,000 is what I was told. Sometimes that we can't afford that, and then obviously you have to have more, but maybe try not to have a lot less than 50,000 processor cells for each processor. Okay, so now we already did the block mesh and the snappy hex mesh in this case, so we already have the mesh ready. Snappy hex mesh can mesh in parallel as well, so we could have just run the block mesh, then decomposed the block mesh, and then meshed in parallel. But I've noticed sometimes you get it makes it harder for snappy hex mesh to find a converged good quality mesh if you do it in parallel, but not always. So if I have the resources to do it on one core, meaning if the mesh is small enough that it can be handled with one core, and the memory of one core, then I will do it on one core. But sometimes I have to do it in parallel, which is also fine. So we already went to the block mesh and snappy hex mesh, so all that remains in this case is to run SimpleFOAM. And OpenFOAM, if we just run SimpleFOAM now, it will just run the serial computation again, and we don't want that. I should show you after we ran decompose par, we got these additional folders called processor 0, 1, and 2, which are the different processors where the mesh is decomposed. Each one contains its own boundary conditions for the fields in that processor, and it also contains the mesh in that processor. So if we run SimpleFOAM here, it will not use these processors, but it will just run the case as we did before. And we don't want to do that. In order to parallelize OpenFOAM, we use OpenMPI. So we use a command called MPI run, and then we specify 3 cores. I think usually you don't need that MP3 MPI run. If you submit the job using the Slurm scheduler, it's aware of how many cores are allocated, so you don't have to necessarily type MP3, but I'm doing it here just for clarity. And then we type the name of the program we want to run in parallel. Now, if I just do this without anything else, it's going to run SimpleFOAM, the whole simulation in SimpleFOAM 3 times. Each of the 3 cores runs the same simulation. It just runs it 3 times, and we don't want to do that. We want to run it parallelized, and almost every solver in OpenFOAM and almost every utility is already set up to be parallelized. So the code is already there. You don't need to do anything. All you need to do is when you execute the command, you add the flag parallel. If I do that, then SimpleFOAM will know that I'm running in parallel using these processor 0, 1, and 2 directories as my kind of base for the data. Okay, so I'm gonna do that. And I don't know if you remember, but it is significantly faster than when I ran it on just one core. We will see how much faster in a few seconds. And I put 3 cores here just as an example. As I said before, OpenFOAM scales pretty well. Using a lot of cores, I've used maybe 500 or so in some simulations in the past. And it's all set up to be parallelized to work with however many you want. And because it's OpenFOAM, it doesn't matter to the cost. The monetary cost, you still have to be wary of how much of the cluster resources you're using and how much has been allocated to you. But the monetary cost is still zero. Okay, it's about to complete. Okay, so I finished in 73 seconds. I believe the one where we ran with one core finished in something like 200 seconds. So it's pretty spot on, 3 times faster, which is good to see. So yeah, that was it. That's the whole process for parallelizing an OpenFOAM case. All you need is that decompose par dict. You tell it how many subdomains you want to split it up to, and then you run decompose par, and then you launch the solver using the same command as you did with one core, only you launch it through MPI run. And these commands, because OpenFOAM is all command-based, as you will have noticed by now, it lends itself very well to writing fairly easy to read job scripts that you can submit to the cluster. You would just type all of these commands that I've been typing now manually into a script, and then you submit that script. The next thing I want to do is, or the next part of this tutorial is implementing new methods. And I think in the interest of time, I want to leave a little bit of time for Q&A at the end. I'm going to talk through it in the instructions document rather than doing it live in the VNC session. But you're not missing out on anything. It would be mostly talk anyway if I did it live. But I just want to talk through it and talk about a few key points that I want people to keep in mind if they get into programming in OpenFOAM and programming your own solver or your own boundary condition or whatever it is. So I'm going to go through, just want to confirm that you can actually see the instruction document that I'm showing. Can someone confirm that you can see the document?
Yeah, it's visible.
Okay, perfect. Thank you. And I see now in the chat that someone got a segmentation fault. We had this problem last time as well. Someone got a segmentation fault with block mesh, and I don't know why. It may be that you need to restart your session or log in to the cluster again. I'm not entirely sure. We were never able to figure it out. I don't think it's anything you have done wrong in the setup, because then that's not a proper OpenFOAM error. That's some other kind of error. So I'm sorry, but I don't know what that means or why. But try and relog to the cluster and see if that fixes it. Okay, so we are in the instructions document, and I'm going to scroll. Oh, I scrolled too far. So we're here, modify a solver. And what we're going to do is we're going to create a new version of the OpenFOAM solver called IcoFOAM. IcoFoam is the most basic incompressible flow solver in OpenFOAM, but we want to modify this solver to do transport of a custom field. Usually, IcoFoam only deals with pressure and velocity, but we want to have a custom field that we solve a transport equation for and see how the concentration of that field spreads through the domain. And again, this is just an easy example. It's not something I do day-to-day basis, and maybe you don't do anything like that either, but I just want to show the basics of how you create a new solver, modifying one that already exists, because the same way as when we run an OpenFOAM case, we copy a tutorial that does something similar and we modify it. When we make a new application, we copy an existing application that does something similar and we modify it. So the first thing I did was to create a new directory where I put my custom applications. I call it Foam Apps. Then I copied this from the VM project directory. That's where all the OpenFOAM source code is stored. I copied this solver called IcoFoam, and I renamed it to my IcoFoam. And this is important. Always, when you copy something, rename everything that has the name of the original solver in it. So because you don't want to, usually on the cluster, you're not going to overwrite the original IcoFoam solver because it's write protected. But if you're on your own system and you installed OpenFOAM somewhere where it's not write protected, you may overwrite it. And even if you don't overwrite it, if you got two applications with the same name, there may be some conflicts. Okay, so we copied the entire folder that contains the source code of IcoFoam, and we called it my IcoFoam. This is just changing some permission so we can execute commands in that folder. So these two lines, I would say, are the most important thing you need to do when creating your own solver. This is going into the make files and changing the name of the executable that we create from IcoFoam to my IcoFoam. And we change the location where we put this executable from the default bin where OpenFOAM puts all its application to a user bin. So we change from foam app bin to foam user app bin. That way we make sure we don't overwrite anything. I also changed the name of the source code file from icofoam.c to myicofoam.c. This doesn't really matter. It's just better for clarity that everything has the new name, so you're not confused with what's the original solver and what's your modified solver. Okay. The next thing we want to do is we want to create a new field. As I said, this new solver is going to be IcoFoam, but it has a custom field that it solves a transport equation for. So there's a file called create fields. It's in this folder that is now called my IcoFoam. And we add this source code where we create this field. We call the field my field. We say that it must be read in each when you start the simulation, and it will be automatically written whenever the control dict tells the solver to write. And then we want to do something with this field. We want to create a transport equation. So I've created a scalar transport equation here for my field. My field doesn't look very nice in a mathematical equation. So for the equation, I just call the field F, capital F. So we got the FDT, nabla UF minus nabla new nabla F equals 0. So let's put this equation in its own file. There is already a file, of course, the source code of IcoFoam already contains a few other equations, transport equations, but we want to put this in its own file just for better readability. And this is the code that we put in that file, and that's basically it. This is kind of nicely illustrates the strength of the modularity of OpenFOAM, in that these few lines, this could have been one line, but it's split up to a couple of lines just so that it's easy to read. That's the entire representation of this differential equation in OpenFOAM. All the code for how to actually solve this equation and how to construct the matrices and everything is already hidden in other classes that we don't need to worry about. We just need to worry about what the equation is. So we're saying finite FVM stands for finite volume method, time derivative plus finite volume method divergence of my field minus finite volume method Laplacian of my field equals 0. And then we just paste this by including this file that we just created called my field equation, where this source code is located, into the source code of my IcoFoam. And you can see that we pasted it. I grayed out a little bit here what the original file looks like. We're pasting it inside the piezo loop before we solve the other equation. So we're solving this equation first. And that's about it. That's it for code modification. OpenFOAM has its own kind of scripting environment for compiling. It's called wmake. So all you need to do is type wmake. Wmake is for executables. If you are compiling a library, the command is wmake libso, which I've written here. If you're compiling a library and forget to put libso, it's going to get very mad with you and tell you that something is wrong. And that can be confusing because it doesn't tell you what is wrong. But remember that if you're compiling a executable, it's wmake. If you're compiling a library, it's wmake libso. So a library would be something like a boundary condition or any other modular component that gets linked to an executable, whereas an executable is the actual solver or tool or whatever it is that you're building. The next thing is I'm just copying here the cavity tutorial. I don't know if you're familiar with the lid-driven cavity test flow case. It's basically just a box with walls, 3 walls, and the top wall has got a flow going over it. That's this tutorial. And in that tutorial, I run block mesh to create a mesh. It's just a uniform square, the domain, so we don't need snappy hex mesh here. I just run block mesh. What we need to do, though, is in the 0 folder, we don't have any initial or boundary conditions for the field called my field. And remember, in the source code, we said that this has to be read in every time step. If we look up here, we said we must read the initial and boundary conditions in every time step. So this file must be present. So we're going to steal the boundary conditions for pressure. We're going to copy 0 from the 0 folder, the boundary conditions for pressure, to a new file called my field. And we're going to modify here again. You see this vector of dimensions that we talked about before. we want to say that my field is non-dimensional. So it's all zeros. And then we want to say on the moving wall, which is the top wall, I will show a little graphic a little bit later so you can get a better grasp of what this looks like. But basically we got a square domain. We got the bottom and side walls are just fixed walls, and the top wall is moving. So that's creating a kind of vortex or swirl inside that domain. And we say that on this top moving wall, this field, my field, has a fixed uniform value of 1. And on the walls, it has a fixed uniform value of 0. And then what we need to do as well is in FV solution, we have to specify what matrix solver we want to use to solve that equation that we just created for my field. I'm saying here preconditioned by conjugate gradient. I think I just copied that from pressure. I didn't come up with that myself. It's with most things in OpenFOAM, you copy and paste and steal things from other places to assemble something that works for you. And then in the FV schemes, we need, because we requested divergence of this field, here we requested the solution, or sorry, the equation contains the divergence of my field. So if I don't specify what it should use to calculate divergence in FV schemes, it's going to complain. So I just said a linear, which is central differencing. I also requested Laplacian, but I think the reason I didn't put anything about Laplacian here is that in the FV schemes, it's set that Laplacian is by default a Gauss linear, I think. So then I don't have to specify, because everything, all Laplacian equation, or all Laplacian operations should be Gauss linear according to this FV schemes dictionary. So I don't have to specify anything in particular for my field. And then instead of running the original solver, we run my IcoFoam. And then we look at the results. So this is what it looks like in ParaView. We have this square, the top boundary here. It's got a fixed velocity going left to right, I believe. And then we got, as we specified, this, we colored it by my field. So as we specified, my field is 1 at the top here, and it's 0 along the walls. And because we got some flow going on here, it kind of diffuses into the domain like so. So that was a very simple example of how you can very easily in a few steps. This would take you maybe like 15 minutes, I don't know, to do this. If you were doing it like directly in your OpenFOAM environment. We've created a new custom solver with an equation of our choosing. And as you could see, how to implement an equation, probably the equation that's suitable for your research is probably maybe a little bit more complex than the one I picked. But OpenFOAM's modularity and the finite volume methods that come with it make it very easy to write out the equation that you want, and then compile it and run it as a custom solver. If you missed something I said during this tutorial and that you can't find in the instructions document, I gave this same course in the spring, and that entirety of that course was uploaded to YouTube, to the HBRC YouTube channel. So you can listen through that if you want to listen to what I said in your own time. I think I said the same thing or very similar things as I did just now in that course. So you can go and look at that if you want to. And again, you also have the instructions document go ahead and bookmark that page or download the document so you have it if you want to use it. All right, well, I don't see any other questions, so I'm going to close here and say thank you very much for attending and good luck with your OpenFOAM experience. It may take a little while to get used to, but it is very rewarding to have the freedom that you have when you're able to modify it as you want. So thank you very much. Bye-bye.